Look up tonight and you'll see stars, thousands of them if you're far enough from a city, and it feels like the most permanent thing there is. The sky has always had stars. It always will. That's the part that's wrong. The sky full of light you grew up under isn't the normal state of the universe. It's a phase, and a short one. Darkness came before the stars switched on, and darkness returns after they burn out. And the dark on both ends runs so much longer than the light that calling our era normal is like pointing at a single spark and calling it the whole fire. What you're about to follow is the entire timeline of the universe, not just where it came from, but where it's going. And by the end, you'll know exactly where this moment, you sitting here right now, actually falls on it. It's not where you think. Let's start in the dark. Roughly 13.8 billion years ago, the universe began, and we know that age with startling precision, because the Planck Space Telescope pinned it at 13.787 billion years, give or take 20 million. For the first few 100,000 years, nothing could be seen. No stars, no galaxies, just a blinding hot fog of particles packed so tightly that light could not move through it. The universe glowed, but it was sealed shut, like being trapped inside the surface of the sun. Around 380,000 years in, everything cooled enough for that fog to clear, and the universe turned transparent for the first time. That light, the light set free at that exact moment, still surrounds us today, and we call it the cosmic microwave background, the oldest light in existence. When it broke loose, it carried a temperature near 3,000 degrees, but billions of years of expansion have stretched and chilled it down to 2.7 degrees above absolute zero. The faint, even hum of warmth that fills every corner of space. And here's the part nobody pictures. After that flash cleared, the lights went out. Completely. No stars had formed yet, and the first ones were still hundreds of millions of years away, which dropped the universe into a stretch astronomers genuinely call the cosmic dark ages, an immense span of pure blackness filled with cold hydrogen gas and the dying afterglow of the beginning. Data from the Planck mission places the first starlight somewhere between 100 million and 550 million years after the Big Bang. Sit with that for a second, because the darkness before the first star lasted longer than complex life has existed on Earth. There's a stranger footnote buried in here too. For a brief window, somewhere between 10 and 17 million years after the Big Bang, the leftover heat of the cosmos sat between the freezing and boiling points of water, which meant room temperature everywhere, all at once. Harvard scientist Avi Loeb worked out that liquid water could have existed anywhere in the universe during that window. The catch was simple. No planets had formed yet to catch a single drop. For a moment, the universe was warm and utterly empty. The first stars ignited after that, and our chapter began. The era we live in carries a name, the Stelliferous Era, and stelliferous just means star-filled. This is the age of starlight, the only chapter where the night sky looks the way it looks to you now. Two physicists built this framework, Fred Adams at the University of Michigan and Greg Laughlin, now at Yale, first in a 1997 paper for Reviews of Modern Physics, and later in their book, The 5 Ages of the Universe. They carve all of cosmic time into 5 eras, and we are standing in the second one. Rather than counting in plain years, they measure in powers of 10, what they call cosmological decades. We sit at decade 10 right now, and the star-filled era stretches all the way to decade 14. Translated into ordinary numbers, the age of starlight should last about 100 trillion years. We are 13.8 billion years into it, which is not even 1% of the way through. We are inside the first sliver of the only era that has stars in it at all. And then it gets stranger, because star formation across the universe already peaked. A major 2014 review by the astronomers Maddow and Dickinson found that the rate of new stars being born hit its maximum about 3.5 billion years after the Big Bang, and has been falling ever since. That grand finale of star birth fired roughly 10 billion years ago. We didn't show up at the height of the light. We arrived on the way down. Before you mourn it, though, understand that the stars themselves refuse to quit. The most common star in our galaxy is not a sun like ours at all. It is a red dwarf, small and dim and absurdly efficient. And red dwarfs make up about 75% of every star in the Milky Way. The smallest of them can burn steadily for up to 12 trillion years. The universe is still so young that not one red dwarf has ever died of old age, which means every single one that is ever ignited is still burning at this very moment. So we aren't standing at the end of the light. We're crowded near the very beginning of it, and that makes what comes next much harder to hold in your head. Let's pull back for a moment, because the scale is the entire point. Picture squeezing the whole age of starlight, all 100 trillion years of it, down into a single calendar year. On that scale, the Big Bang went off less than an hour ago. The sun forms somewhere around minute 22, and this exact moment lands at about minute 53 of January 1st. The sun dies before the first day is over. The last star won't gutter out until New Year's Eve, 12 full months later. We are 53 minutes into a year-long story, and every empire, every life, every star anyone has ever wished on happens inside those opening 53 minutes. Here's the thing about that calendar, though. Once the year ends, the universe doesn't stop. It keeps going for an almost unimaginable stretch, and it spends all of it in the dark. When the last stars fade, around 100 trillion years from now, the Stelliferous era closes, and the third chapter opens, the Degenerate era. That name earns itself. What survives are the corpses of stars, white dwarfs and neutron stars, brown dwarfs that never grew massive enough to shine, and black holes, with no new stars forming to replace them. Now and then, two dead brown dwarfs might collide and strike a brief new spark. But Laughlin calculated that, in a galaxy our size, this happens maybe once every quadrillion years. The lights are effectively off, and whatever remains just smolders and cools. And then matter itself may start to come apart. This is where things turn uncertain, and the honest version deserves to be stated plainly. Many physics theories predict that the proton, one of the basic building blocks inside every atom in your body, isn't perfectly stable, and given enough time, it decays. The estimated time scale runs near 10 to the 34th power years. Nobody has ever actually watched a proton die, and that matters, because experiments deep underground in Japan, at a detector called Super Kamiokande, have only confirmed that if protons fall apart, they survive at least 10 to the 34th years. This is a prediction, not a verdict. But if it holds, then somewhere around 10 to the 40th power years, the dead stars themselves evaporate. The white dwarfs and neutron stars and planets and anything else solid slowly dissolving into radiation and stray particles, until matter as we know it stops existing. Once that finishes, a single kind of object is left to run the universe alone. Black holes carry the fourth chapter, the black hole era. Across an expanse stretching from roughly 10 to the 40 years to 10 to the 100 years, black holes stand as the last large structures anywhere, with everything else long gone. Even they are not permanent. Stephen Hawking showed that black holes slowly bleed away energy and shrink over timescales that flatten the mind, and a black hole the mass of our sun would need about 10 to the 67 years to vanish completely. The largest supermassive black holes, the giants anchoring the centers of galaxies, take up to 10 to the 100 years, a 1 followed by 100 zeros. A genuinely new twist landed in 2025. Researchers at Radboud University, led by Heino Falke, demonstrated that this kind of evaporation is not reserved for black holes at all, because anything with mass slowly radiates itself away. By their math, white dwarfs evaporate in around 10 to the 78 years, far sooner than the older estimates assumed. As Falk put it, the ultimate end of the universe will therefore come a lot faster than expected, but fortunately it will still take a very long time. A lot faster, and still a number so vast it carries no meaning to a human mind. When the final black hole evaporates, the fifth and last chapter begins. It's called the Dark Era, and it is precisely what it sounds like. Past 10 to the power of 100 years, nothing structured remains. No stars, no planets, no black holes, just a thin, freezing scatter of leftover particles, stray electrons, and lone photons stretched to enormous wavelengths, drifting through an ever-widening dark and growing colder forever. Physicists call this heat death, which is the opposite of fire. A universe spread so thin and chilled so deep that nothing can ever happen in it again. No light, no warmth, no change. That state never ends. It is the rest of time. Take the full shape of it now. Darkness before the stars, one blaze of starlight in the middle, and then darkness again. Not for a stretch, but effectively forever. The light is the exception. Darkness is the universe's natural condition, sitting on both sides of us. None of this is fully settled, and the honest version turns out to be far more interesting than a tidy one. Proton decay has never once been observed, yet the end of matter leans on it. Across 2024 and 2025, a sky survey called DESI turned up the first real hints that dark energy, the force shoving the universe apart, might be weakening over time instead of holding constant. The signal sits near 4 sigma, strong but short of certain. Should it hold, the entire far future could rewrite itself, and the astrophysicist Priya Natarajan stated it without flinching, saying our fate may not be as lonely and desolate and grim as we imagine. We are watching this question shift in real time. The shape stays the same regardless. Dark, then light, then dark. Lawrence Krauss and Robert Scherer identified what might be the loneliest fact in the whole story. Because the universe expands faster and faster, in about 100 billion years, every galaxy beyond our own neighborhood will have raced past the edge of visibility. Whatever astronomers exist then will find only their own island of stars adrift in an apparently empty void, with no way left to discover the Big Bang at all, the evidence simply gone. Which means we are not only living in the Liti part of the story, we are living in the one part where you can still reach back and find how it all began and work out how it ends. The stars feel permanent. They are not. You are sitting in the brief, bright window between one darkness and another, and almost no one across the universe's entire lifespan will ever get this view. Most of time is dark. We got the light. Thanks for watching.